This video is a review of hypothesis testing. So for hypothesis testing that we covered in Statistics 1, you recall that we have to do the setup of a hypothesis test by identifying the null hypothesis and the alternative hypothesis. The null hypothesis, recall, always has an equal sign. Back in Statistics 1, we used very clear symbols like less than or equal to, and greater than or equal to in order to create a very clear opposite or complementary effect with the alternative. But technically, in a statistical hypothesis test that we run, the null hypothesis is just an equal sign. It's assumed to be one of these symbols, but we just write an equal sign. The alternative hypothesis is what determines the test, whether we're right-tailed, greater than sign, not equal to, two-tailed, or less than, which is for left-tailed tests. So here are our three setups. We always have a setup where they're complementary. There are no gaps in the number line. And this is the claimed value K. Here are some English translations to help you if you struggle with translating inequalities. Greater than or equal to is literally a greater than or equal to sign. So notice that the null translation is on the left side and the alternative statement translation is on the right side. So less than, below, fewer than, shorter than, all talk about a less than sign. When we are doing a p-value to help make our decision on the test we are running, the comparisons we will use is if the p-value is really, really small, smaller than our set alpha level, we'll reject the null hypothesis. Recall that the standard alpha level is 0.05, although it can be other values. If it's not given, we default to 0.05. If the p-value is large, specifically larger than our alpha level, we'll fail to reject the null hypothesis. Let's try some examples, and we are going to be doing these in our Guru, not out by hand. So in auto racing, a pit stop is where a racing vehicle stops for new tires, fuel, repairs, and other mechanical adjustments. The efficiency of the pit crew that makes these adjustments can affect the outcome of the race. If your pit crew is too slow, then that takes more time out of your ability to get back on the track. A pit crew claims that its mean pit stop time for changing 4 new tires and fueling up is less than 13 seconds. A random sample of 32 pit stop times has a sample mean of 12.9 seconds. Assume the population standard deviation is 0.19. Is there enough evidence to support the claim that the pit crew is stating that their mean time is less than 13 seconds? All right, couple things. Hopefully you have downloaded this PowerPoint from your course and you have it in front of you because you're going to need it to reference the numbers when we're putting this in our Guru. Because unfortunately, I can't show you this PowerPoint and our Guru at the same time. So I need to write these down so I have them. Working on that now. I have my claim less than 13 seconds. So I am going to set up my null hypothesis. Nope, I can write this down for you guys. So my claim that's being made is less than 13 seconds. So I'm going to say I have the null and the alternative. These are my labels. We are working with a problem that is talking about means. Okay, so notice it says means. So I know that I'm using mu as my symbol. And less than 30 seconds, because this is less than, remember, the equal sign is what goes with the null. So that means my claim is the alternative. So less than 13. And my null is just equal to 13. Technically, it's greater than or equal to, but remember, we are moving on from our intro stats, And hypothesis tests just use a straight equal sign. So that's my setup. I have mu equal to 13 and mu less than 13 for my alternative. Don't forget to label that the alternative in this situation is your claim, because remember, we're going to have to make a conclusion at some point. Now, my sample size, n, is 32 times. Okay, so I know I need to know my sample size. The sample mean, x bar, came out to be 12.9. The standard deviation that's given is the population standard deviation, so that's sigma is 0.19. Remember, the fact that sigma is known or unknown is important. It helps us realize whether we are using z test statistic or a t test statistic. And we want to make note that our alpha level is 0.01. Okay, let me switch to our guru now so that we can learn how to use our guru to do hypothesis tests. Just give me a moment. Here we go. This should be it. Yes. Alrighties. So we don't have to import the data. We can actually use the summary statistics from the word problem to complete the hypothesis test. So we're going to head over to analytics, analysis. We are working with means, not proportions. So mean inference, and we will get to more than one population. But right now we're just in review. We're reviewing hypothesis testing from stat 1. So we're going to one population. Don't need to upload a data set. We're going to work in these boxes here, the summary stats. Our sample mean of the 32 pit stop times was 12.9. The sample standard deviation was not given, but the population standard deviation was 0.19. Sample size is 32 pit stop times. What is the label of the mean? Well, the mean, what is the units? The pit stop times were in seconds. So I'm going to write seconds here. Soon we will get to what the heck these are for. They are important, but we're not there yet. So let's hit test of hypothesis. We can do confidence intervals in here too, but we're working on hypothesis testing right now. Change our alpha level, our significance level, to 0.01. The alternative hypothesis, as we know, determines the test, and we set it to a less than 13 seconds. That was the claim. Now, because sigma, population standard deviation, is known, we will use a z statistic. Let's hit our eyeball. So this tells me that the p-value is 0.001. 0.001 is less than the alpha. Let me write this in. Let's point out what we're looking at here. So my p-value, 0.001, is less than alpha, which is 0.01. And therefore, since my p-value is really, really small, I am going to reject the null. Now, rejecting the null is, in a way, saying that it's not true, so to speak. And that means since our claim was the alternative hypothesis, the less than 13, we would say that we have sufficient evidence to accept the claim or to believe the claim, or we have sufficient evidence to reject the null, therefore our claim, we believe, is true. Okay? Let's look at our next example. Back to the PowerPoint. Next example, a used car dealer says that the mean price of used cars sold in the last 12 months is at least 21,000. You suspect this claim is incorrect. You find a random sample of 14 used cars, and you find that the mean price of those 14 used cars is $19,189, with a standard deviation of 2,950. We want to know if there's enough evidence to reject the dealer's claim that he says that the mean price of his cars are at least 21,000. And we're using an alpha level of 0.05. And a statement is made that the population is normally distributed. Let's point out some of the things that we need to take notes on. So we need to do our setup. We have the null and the alternative hypothesis. We are still in the means, so we're still using mu. We were in proportions, we'd use p. We have to identify the claim. Claim is at least 21,000. So if I have to go back to that chart where it translated the English into a mathematical symbol, at least, sometimes translating it using your money really helps. So if I have at least $35 in my pocket, that means I don't have less than $35. It means I might just find some more. So at least, greater than or equal to. Since it has an equal to sign, that means it goes in the null. I don't know where I got, oh, because I changed it to $35 in my pocket. I'm like, where did the 35 come from? Greater than or equal to 21,000. And we put the opposite in the alternative, which is strictly less than 21,000. This time, the claim is our null, not our alternative. So whatever happens in the test, rejecting or failing to reject the null, directly affects what we believe about the claim. We will label the sample, n is 14, sample size 14, which is less than 30, which means that if we didn't know that it was normally distributed as it states, then we wouldn't be able to complete the test with any validity. Remember, we either have to have a sample size of 30 or more, or know that our population is normally distributed. Our X bar is 19,189. Our standard deviation, now, remember, we have to identify, is this S or is this sigma? But if you read this sentence, the whole sentence is talking about the sample data. And at no point does it reference population or all the data. So this is S, a sample standard deviation. And we have our significance level of the default of 0.05. So now I'm going to write these numbers down real quick so that I have them when I jump over to our guru. And you should do the same if you don't have the PowerPoint up. S2950 and alpha. Okay. Heading over to our guru now. We can keep this tab open if you're working. It'll just create new tabs when we do another problem. So I'm going to go back to analysis under analytics, mean inference, one population. My sample mean was 19,189. Population standard deviation was not offered this time, but the sample standard deviation was 2,950. Sample size was 14. Variable units is dollars. Put the dollar sign. I am testing a hypothesis at 0.05. The alternative is also a less than sign. And the claim was 21,000. Now, I do not have a large enough sample size, and I only have the sample standard deviation, so I need to use the t statistic. Really important that you remember to check that. Eyeball. My p-value is it rounds to 0.02. 0.02 is a p-value less than 0.05. So again, I'm going to reject the null hypothesis. And I would also be saying that I don't believe the claim. That no surprise, we don't believe the car salesman's claim. Let's try another one. Here we go. A researcher claims that 51% of US adults believe, incorrectly by the way, that antibiotics are effective against viruses in a random sample of 2,202 adults. 1,161 say antibiotics are effective against viruses. Alpha level of 0.1. Is there enough evidence to support the researcher's claim? All right, now let's take a look at this problem. Now, in this problem, I don't see the word mean anywhere. Plus, remember, one of the biggest indications that this is not a means problem, this is a proportions problem, is that standard deviation is not given. And the only way to use calculations with mean problems is if you have a standard deviation or a data set to calculate it from. So it's one of your biggest hints that this is a proportion problem. So we are working in proportions. Let's start with our null and our alternative. And this time our population parameter is P. Now, the claim that's being made is that 51% adults, the researcher says that exactly 51% of adults believe incorrectly that antibiotics are effective on viruses. So that's an equal sign. And since it's an equal sign, it goes in the null. Now, remember that we don't put percents in hypotheses, we put the proportion. So just translate the 51% into a proportion, 0.51. The opposite of an equal sign is a not equal to. So we're saying that the researcher's claim is not believable if the proportion is less or more, and specifically significantly less or more. Now the sample size is 2,202, so that's N. 1,161 is what we call X. It's the part or the count of those who believe that antibiotics are effective. So that means our sample proportion, P hat, which is calculated by X over N, part over the whole, would be calculated by doing 1,161 divided by 2,202. So I don't know if our guru is going to need that, but in case it does, we'll find out when we get into our guru. If I divide it in my calculator, I get approximately a sample proportion of believers that antibiotics works on viruses to be approximately 0.53. Now, our goal is to run a hypothesis test to determine whether 53% is significantly different from 51%. There's no way to just eyeball it and say, which is why we have these tests. So all I'm doing right now is writing down the data that we have on here so that I have it for when I need to type it in. Okay. I'm ready. Oh, alpha is 0.10. I've got to remember that because that is not the default. So I'm going to need to change that when I get into our guru. Let's flip back to our guru and do a proportions one. Here we go. Again, under analytics, under analysis, this time select proportion inference for one population. Now, for proportions, I am going to have to fill out a little bit more. So my factor, I need a factor label, even though I don't have a data set. So my factor label is going to be, let's see, what the heck were we working in again? Oh, antibiotics believers. So antibiotics, and we're talking about believers. Success is those who according to the proportion, is those who believe antibiotics work for viruses. So believe antibiotics for viruses. My sample size was 2,202, way bigger than 30. Not that 30 is even a magical number for proportions, because it's not. Remember, the test to make sure that in a proportions problem that we're good to go is multiplying n times p, so 2,202 times 0.51, and making sure that that's bigger than 5, and doing the same for n times 1 minus p. With a sample size as big as over 2,000, that is definitely going to pass that test. Number of successes is that X value, so 1,161. Our guru is going to calculate the proportion of success for us. Now, the proportion is the notice how this fills in, proportion of portion of those who believe in antibiotics for viruses. I mean, I probably could have worded that better. Our confidence level, oh, we're not doing confidence intervals, so skip that. Here over the hypothesis test, our significance level is 0.10. Our alternative was a not equal to sign. Now this explanation point equal sign, that's actually used in the R language. That's how you write not equal to in a language called R, just like there's C++, Java, Python. R is another language of programming. And that's why this is called R Guru, because R is the programming language, which is actually what is driving all of this to work. And we're saying that we are testing that this is not equal to 0.51. Let's hit our eyeball. So, what happened here? Let me go back to basics. Oh, I forgot to click Z statistic. Whoops. I was like, why didn't the hypothesis run? Notice that the probability of success, or the sample proportion p hat, was automatically calculated, which is what we estimated, 0.53. I just needed to click that. Now we're ready. Let's hit the eyeball. Ah, there we go. That's what I was missing. So my p-value is 0.105. Super close to my alpha level. Recall my alpha level is 0.10. This test is not significant. It's also giving you a conclusion. It's telling you, well, the p-value, even though very slightly, is larger than our significance level, which means we are going to fail to reject the null hypothesis. And that means that we do believe the researchers claim that 51% of Americans believe that antibiotics actually work against viruses. Now that concludes our review for hypothesis testing. I'll see you next time.